one solar cell is on top, another is on bottom. So in this way, you can use the 4-terminal device, and maximum spectrum of sun can be utilized in this one, and we can reach more than 30% of efficiency. On the right side, you can see the 2-terminal device. This is you can electrically connect these two cells in together by using a tunnel junction of some oxide layer in between, very thin oxide layer, and then they are connected in series. But the drawback of this one is you have to mesh the current, because when a series connection is there, the top cell and bottom cell should produce the same current. So current mismatch might be an issue, because the current will depend upon the spectrum which is absorbed by the particular solar cell. However, the advantage is it has only 2 terminals, so easy for module fabrication. So in this sense, for the bottom cell, I think silicon could be the best material, and most of the research teams are considering that. But for the top cell, 3-5 semiconductor are being used since long time, but they are expensive. So they are used, their application is limited to the space or very high end application, but not for the standard one sun condition and your rooftop. For this one, recently introduced material which is perovskite solar cell, they can be used, but there are some hurdle for this type of solar cell, mainly because of the stability and their reliability. Their lifetime is very low, and then people are working to encapsulate them so that their lifetime and then reliability can be improved. And we are at Ceres also working on this project of more than 30% cell efficiency using perovskite on top of silicon solar cell. Till now, I discussed different solar cell technology. Since I mentioned you that we work on PV module technology, and I'm heading this group. So in this one, our main focus is reducing how to reduce the levelized cost of electricity. So if we can make a very high efficient solar cell, it is until not successful until we uh, pack this into a form of module, and which is very high efficiency. So there should be some losses from going from solar cell to a full size module, because the working environment of the solar cell has been changed. Earlier, it was just working in air, and you can optimize it with respect to that, and then it can get very high efficiency. But you have different layers of material in the module, and you have so many solar cell connected together, so all affect the performance. So our main job is to decrease these losses and maximize the power, and at the same time, the reliability, which is the prime concern of module, is the main factor PV module researcher work on, because all these material which is used in module fabrication is responsible uh, for a highly reliable module. So all these are the listed topic which my group is working on. Just to give a brief idea that how a module structure look like, you can see the solar cell which are interconnected by a copper ribbon in between. Then you have a encapsulant which is working as a cushion, as well as a like an encapsulant binding all the material. And there is a top cover which is always a glass. Rear side cover can be a glass or a polymer, and then to provide all these things strength, you put frame around it, and then junction box is to tap the external connection out. So for this one, I'll just briefly go through few slides so that how we achieve this to go for high efficiency module. In this one, in 2015 or before that, we use 3 busbar solar cells. So for a 6-inch wafer, around 3 busbar was there, 2 to 3 busbar. 2010, it was only 2 busbar. So there is one obvious way to increase the power is reduce the resistive losses, because these all like metallized and conductor carry the current, and then there is some certain resistance, and this will give you I square R loss. So if we increase the number of these bus bar, then we can reduce the losses, because the paralleling the current, then current in each wire will reduce. And then similar thing can be done by using half cell. If you cut this thing into half cell, then current is half, so I square R loss will be like a reduced by 1/4. So 75% losses will be reduced. You can see in the graph also that you can easily increase performance by 4% by just doing this thing from a 3 bus bar baseline. This we achieved in 2016, all this thing, and this is now industry baseline. Then rather than using a flat bus bar where the light, whatever light is coming on the bus bar, it is reflected back and go into the environment. So it's lost from the power generation point of view. But if you use wire instead of bus bar, so anything coming at certain angle, because in top there is a glass, so there is a like a interface between glass and air. So anything more than total internal reflection angle of glass and air, which is around 41 degree, that light will be reflected back from the top surface and again hit back the solar cell. This way you can increase some amount of light, so it can increase your performance by 1 to 2%. This is one way to increase your current. And then you can use many wire, like as many as 9 to 12 wire is now is in industry standard. Some companies are using this technology at the moment, and we made this thing in 2017. Then further PV module design comes like a if you see my previous picture here, you can see there is a gap between two solar cell, because you need to connect top of the solar cell to the bottom through a ribbon, and you cannot go zero gap. So whatever light is coming in this gap is lost because it is passing through the other side. So to remove this, to reduce this loss, what we can do, we can put this solar cell into in a form of single, like a one strip over other. So for this one, you cannot use full solar cell. So we can cut solar cell into 5 or 6 pieces and then stack them together using some material. So there is no more no more need for wire to connect strip to strip, which in conventional module. In this way, you can see the module looks like almost black, and it can generate power from all around the module. So you can increase the power by 10 to 15% using this technology. Then, as I mentioned earlier, the sum of the cells, high-end cells, are bifacial. What is the advantage of bifacial? It's like you can see it looks like a same from both sides. That means in traditional cell, on one side there is a full metal. Here, the electric contacts, although on the both side, but it can accept light from both sides. So it has two faces. That's why we call it bifacial. Advantages are occurring in the field. If you put this kind of module, then traditional module can get only the light which is coming on the front side. But this kind of module can get light from the rear side also. You can see some diffuse light or any light which is reflecting from the ground can be captured by the rear side of the device. So this way, you can increase the module performance in the real world. On your rooftop, if you put some white paint on the rooftop, so this is very reflective. This will be very reflective, and you can increase as much as 30% of your power. This is huge amount. And also you can use this kind of module in a vertical mounting structure, because it can work from both sides. So in the morning, one face of this module can accept the light, and in evening another face can accept the light. So this way it can use as like a fencing. Suppose you want to use it as like a for your rooftop fencing, or your like a garden fencing. All these things can be used. So these are few advantages. Some companies are already producing. Actually, outside India, almost every company has this product. In India, only Adani has this product. They are manufacturing in Gujarat. Now, some application of the PV. Till now, I discussed all the technology, that how they have been evolved, and then how researchers are improving them. So, in terms of application, you have different type of application. For example, rooftop or ground mounted system. This one you put it on your roof, and you can connect it to the grid. Of course, there will be some system which can be without grid. You can use your own system, don't connect to a grid, just rely on the battery and then PV. This is also possible. Or most of the Sorry, there's some. Okay. Okay. Yes. So the other way, which is most prominent at the moment, is a large PV plant, and it can be as big as 1 to 2 gigawatt, which could be like like kind of a city, small city, just like you can see in the picture. You can have plenty of module, like several thousands of the module. Then there is one application which is building integrated application. You have this two type of thing is building assisted PV, which is on top of the device. You can see that existing house, if you attach some PV, this can be termed as building assisted or building associated PV. But if you integrate building structure into the PV, then it's called building integrated PV. For example, you can see this building. You see the front side of the tiles, they are PV module actually. It looks like a tile, but this is uh, these all tiles are PV module and are part of Copenhagen International School. And this way you can utilize your vertical surfaces. If you are in a city, you have limited land, limited roof of space, then this kind of vertical space can also be used for some PV application. Then another new application recently emerged is like a floating PV. You have a lot of reservoir and see all the places can be utilized to put the PV. The advantage is whenever you have some hydropower plant, you have a big reservoir. So anyway, you have a grid. You can put your PV there, and you can connect to the same grid. So it can effectively save the cost. And there are already few systems realized in different part of the world. We also have one megawatt system in Singapore, which is test bed, and we are handling that one. You can see different example in this slide. Then recently, some people even started using photovoltaic together with agriculture. So you can see the left picture is actually a bifacial module. You can put it in vertical form, and you can use it as around your field, or you can use it in different like a way. For example, some of the crop need limited sunlight, then you can use partially shading from the PV, and this can be well going all together with the agro-photovoltaic. Recently, this National Institute of Solar Energy in Gurgaon, they launched this program to explore the potential in India for such kind of application, which is some kind of futuristic approach. Okay, so that was all from my side. Now, just to summarize, uh, as you saw, the solar PV is booming, and it will be a $1 trillion industry. And crystalline silicon, as is now, is 94 more than 95% of the technology is based on crystalline silicon, and it will remain 10 to 20 years at least until there is some new material comes with a lower cost, which I don't think is so easy. Then holy grail for PV, we should achieve by 2025 a lower cost module with a very high lifetime and very high efficiency. So there is still room for improvement for next couple of years in a standard silicon technology, and we can use such kind of PV in different applications. The first application, land-based, is like a traditional one which we use mostly, but there are other applications which are being explored all around the world: BIPV, floating, agro PV. So with the new innovation, I'm pretty sure that the electricity from PV will be much cheaper than then grid electricity or conventional sources like a coal or any other different sources, oil-based plant or gas-based plant. And these two technologies, solar PV and wind, are major technology which can help us in fighting global warming, because both are renewable, clean energy. So transition to sustainable global energy system has already been started, and this is in interest of yours for your career as well as for your country. So you should contribute to your country as well, and please get involved. This is from my side. Future energy mix. You see, this was in 2003. We can see that in 2020 still we have only very tiny part of this solar energy. This is with yellow color. But now I believe this. Earlier it was supposed that it could happen that maximum energy will be by 2100 will be used by solar, but now it will come even faster than that. So uh, definitely there is a time to come. The solar energy will be boom even at faster pace, and India is like a best suited location for this because we have plenty of land, plenty of sun all over the country. Thank you very much for your attention. If you have any question, I would happy to answer. Thank you.
Thank you so much, sir. I mean, this is definitely a very like intriguing talk, very technical, and I mean, there should be many questions. I'm pretty sure, but the thing is, like, we are pretty much reaching to the time.
Okay.
So I'd just ask one question from my end, actually. So no
Yeah.
more technical questions. It's just because it's more like a career outreach kind of a workshop. So
Okay.
what do you think for the students and the new researchers, that what is the scope for them in the PV market, like PV, like the global outreach for PVs, if anybody thinks in a career of that thing?
Okay. So there are two paths of this one. If you want to go for industry, or you want to just do research in the lab. So both the places you have a significant scope. Uh, in India, although there are not many research centers, only few, couple of IITs are working on this, and there is one National Institute of Solar Energy in Gurgaon, IIT Bombay, and CPRE.
এ
They are
মঞ্জু
also,
বাইরে কোনো মেলা আছে নাকি
and
একদম অন্ধকার করে দিছে
in addition to this, because there are several labs around the world, they are working on all high-end technology. So this is a good topic for research, and at the same time, you will be like a feeling some satisfaction that you are working for some real life problem, which is like a global temperature is rising and you are working for the clean energy. Our Prime Minister Modi and everyone says like this, that this is time for India to go for clean energy, Paris Agreement, all these things. So enough scope for a student to go into this one. It's not like now we are already done everything. It's a lot of things need to be done in a couple of year, or maybe in a few decades. Next few decades will be for the solar only. And industry wise, there are a lot of PV plants. Every year we put almost 9 to 10 gigawatt in India, and manufacturing wise, module have 4 5 gigawatt, but cell are still limited. But believe me, in future, in next couple of years, there will be many companies where you can find the opportunity to work on the real industrial devices. So it's both way. Either it is in research center or it is in PV industry. Both ways there are opportunities. Yeah, I think
Yes,
I
sir.
hope this.
Yeah. Thank you so much. I understand, like, there is a lot of scope in photovoltaics in near future, and many people will be definitely interested to actually reach out to you, talk to you, and understand more about this.
Yeah,
So, uh, def-
fine.
yeah. So, thank you so much. I personally thank you for your time and this wonderful talk. And we'll definitely record everything and put it on the college website so that people can understand some of this more. We'll definitely share it with you.
Okay,
And thank you so
thank you
much,
very
sir. So
much for.
I'll switch over to the next speaker. And
Yeah,
thank you so much, sir.
okay.
And
থ্যাংক ইউ
yeah. JB sir, can you transfer the host to me? I mean, you can just select me and transfer the host to me, I think, so that I can share as well. So our next speaker is Dr. Tanmay Basu. So I can see he's already here, and I'll just transfer the sharing rights to him. So JP sir, you can select me from the panel of the this is participants, or you can just select my image, my video, and on the right you can see you can transfer the host rights. Uh, we can't hear you, sir. So I can't just.
I tried to.
So can you select my image, my video?
Yeah, I'm just doing that.
Yes. So if you click on that, there is a button to transfer host. Is it?
Yes, I.
Okay, great, sir. I have it. Yeah, thank you so much,
Okay.
sir. Yeah, really appreciate that.
Yeah.
And thank you so much, sir. I mean, we definitely hope that you can enjoy rest of the discussions and like
Right.
from my NUS also. So we'll talk more after the sessions maybe. Thank you so much, sir. So I'll switch over to the next speaker, and I'll just give a very brief idea about Tanmay, because Tanmay have been very close to me as a friend for several years, and so Tanmay is a research fellow at the Center for Advanced 2D Materials, which is the Graphene Center in NUS. It's very famous. And he's also part of the Center for Ion Beam Application, which is CIBA in the Department of Physics, National University of Singapore. And he has been, he did his PhD from the Institute of Physics, Bhubaneswar in 2015, and then went on for a postdoc in the prestigious CNRS in France. From there onwards, he's a research fellow at the Center for Advanced 2D Materials at National University of Singapore. And I'll transfer the hosts to Tanmay, and just allow me a minute on this. Okay, Tanmay. So welcome.
Okay. Am I audible? Can you hear me?
You're audible, Tanmay.
Okay, great.
Yes.
Okay. Okay, that's good. Let me check if I can share my screen first. Okay. I think.
Great. Yes, we can see your screen, Tanmay. I'll request all the viewers, everyone, to kindly turn off their video and put your speakers in the unmute mode. And just as a courtesy to our speakers, because otherwise it will continue to happen like this. We will like to and fro, like juggle between various screens. Thank you so much. Tanmay, over to you.
Okay, thank you, Amit. Thank you for this nice introduction that you have given for me. Let me introduce myself. I am Tanmay Basu, as Dr. Amit already mentioned, and I basically affiliated to two centers. One is Center for Advanced 2D Materials, and the other one is Center for Ion Beam Applications. Both these centers are under National University of Singapore, Department of Physics. Now, I would like to deviate a little bit from the previous talk where Dr. JP shown about different aspects of the solar cell or photovoltaics and the recent trends about that. But I would deviate slightly from that part, and I would like to talk a new field of research, which is ion beam based research. And I would like to correlate later at the end of my talk how we can use ion beam technology to solve some of our existing problems apart from the energy crisis. Okay, let me start with the outline of the talk. So I would first introduce the facilities that I use in Center for Ion Beam Applications, which is the main fabrication center for this kind of application that I do in our lab. And then I will talk about, because this talk centers around the ion beam modification of materials, I will talk about the ion beam interaction and how it can be useful and how it is different than electron matter interaction, right? And then I will go some material analysis that we can do using ion beams. Then some of the applications of high energy ion beams that we can do in Center for Ion Beam Applications. After that, I'll enter the main theme of the talk, which is the interaction between ion beams and graphene. And from there, I'll move to the application of focused ion beam approach to create some structures in graphene. And then I will describe what is the future prospects of this kind of applications. Okay, since probably there will be many students here, I would like to keep the try to keep my talk as simple as possible. And if there is any question, please interrupt me at the end of the talk. Thank you. With this, I would show a glimpse of the facility that we have in Center for Ion Beam Applications. So we have an accelerator there, which works with terminal voltage of 3.5 mega electron volt energy. And this is called singletron accelerator. This is basically to create MEV energy ions of basically light ions, which is particularly helium, then protons or hydrogen, then nitrogen, these kind of light ions particularly. And if you look at the schematic of the accelerator, you'll see there is a big tank, which is the tank where you keep the ion source, and you have the acceleration column inside this tank. And these are well insulated using sulfur hexafluoride gas, so that you don't get any electrical contacts outside. From there, you create the energetic ion beams. So basically, energetic particles, charged particle with positively charged ions, and then you accelerate them through this beamline, which now goes after that, which goes through this bending magnet, which is called 90-degree magnet. And from this magnet, using this magnet, you can actually filter out or choose different kind of ion species. For example, if you want to use hydrogen, if you want to use helium, or if you want to use nitrogen, you can put a particular magnetic field and you can extract the particular ion species. From there, you have different, you have a switching magnet, which is used to sweep the beam into different beam lines. We have 6 beam lines, as you can see. From the left to the right, we have total 6 beam lines, which are working at its fullest extent. Now I'll start from the left and describe a little bit what are the studies we do with all these beam lines. From the left, we have called ion beam analysis beam line, where we can do Rutherford backscattering spectrometry, and then we can do PIXI, which is particle induced X-ray emission, these kind of studies. Both of these studies are related to compositional analysis of the materials, or you can measure the thin film thickness, or this kind of study. PIXI can be used for finding out trace amount of materials or elements inside your samples. The next beamline, which is called radiobiology beamline, and this is basically dedicated for cancer research, which I will describe in a minute later. After that, we have another beamline, which is called proton beam lithography, or proton beam writing facility. And in fact, I would like to say here, in this beamline, we can actually focus down a 2 MeV proton beam up to a size of less than 10 nanometer, which is world record no other lab can manage to this extent to focus a beam of this energy at this kind of small size. So this is a big achievement for SIVA, of course. After that, we have another beamline which is called cell imaging beamline, and there you can put dead cells basically inside this beamline, inside this chamber, and then you can do different kind of analysis, which I will show later what kind of analysis you can do. After that, we have a small chamber where we can do RBS, which I mentioned earlier, and then you can do implantation also, which is one of the focus for this kind of beamline. After that, the next and the last beamline is called a high resolution RBS facility. RBS means Rutherford backscattering spectrometry. And in this beamline, we have ultra high vacuum condition where you can actually do compositional analysis of a very thin sample. For example, the depth resolution of this kind of beamline is less than 1 nanometer as well. So you can actually do a composition analysis of less than 1 nanometer thick sample. Okay, so if you look at this, the plot where we have divided different kind of segments that we do, or different kind of research segments that we do in SIVA, you can see a big chunk of research is dedicated for material characterization, which is RBS, PIXI, and there are other techniques we do. Apart from that, which is recently coming is biomedical application part. Which I will tell later what kind of biomedical application we can do. From there, there is a lithography part. You can see here nano imprinting lithography, or this is done by using proton beam lithography technique, which we have already in our lab. Then there are micro machining or microfabrication you can do with silicon micro machining using this beamline. I mostly work with this small part, which is micro and nanofluidic applications, which I will tell how we can use ion beam for microfluidic or nanofluidic applications. Okay, with this, let me show some of the pictures of the beamline. You can see here. So this is the beamlines that I talked about earlier, and you can see there are these are the big beamlines which are coming out. These are the end station where you keep your sample and do your analysis. The bottom image is basically called quadrupole magnets. These are used for focusing the beam to a very small size. Okay, the next one is I will talk about a little bit how ions and electrons interact with material. So this is an example or the simulation of 2 MeV proton and 50 kilo electron volt electrons going through a biological cell. And you can see the 2 MeV protons go almost straight without much of scattering. Whereas if you compare that with the electrons, you can see immediately that it scatters a lot, and the beam spot spreads over more than 100 nanometer. While if you look at the proton beam, you can see it is confined within 10 nanometer of beam spot. So that is the beauty of high energy protons, that you don't create too much scattering. Your beam is more or less of the same size that you start with, and you can create very tiny structure, and you don't create proximity effect or these kind of problems that happens in case of electron beam writing. Okay, so next topic, I'll show how we can interact or how the ion interacts with a resist material, which is normally positive resist called PMMA, which is kind of acrylic material. And then when this 2 MeV proton beam goes through this kind of PMMA, you can see it loses energy. Sorry. Okay. It loses energy through the interaction with the nucleus of the atom, and it loses energy through the interaction with the electrons present in the atoms, right? Atom in the target material. And there is a plot. You can see when it interacts with the nucleus, it creates vacancy because it displaces atoms in the target material, and then you create vacancy defects. While it interacts with the electrons in the material, and then it gives ionization loss as well. So in the plots, you can see it is more or less linear with depth. I mean the energy loss of the protons is more or less linear as a function of depth. but it jumps at the end of the range, right? So this jump or this kind of sharp peak at the end of the range of the ion is called Bragg peak, and this happens for particularly this kind of high energetic ions. Now, this Bragg peak can be useful for many for many applications, and I will talk about that later. So this part I will discuss mostly about characterization techniques that we do in SIBA mostly. So you can see scanning beam, which is passing through annular detector, which is RBS detector or Rutherford backscattering detector. From the name, you can see this actually detects the backscatter ions, which hits the target material and gets reflected back to the detector elastically, right? And there are also Pixie detector, which is scintillation detector, and those are used to detect the X-rays. And these X-rays are coming out because of the interaction of the ions and the electrons. When the electrons from the core shell of the atom are knocked out and the higher shell electrons are jumped in this lower orbits, then you will see emission of X-rays. And those X-rays are detected with this kind of Pixie detector. And from there, this spectrum will be the fingerprint of a particular element in that material. So you can do elemental analysis using that. After that, we have another detector, which is called transmission or scanning transmission ion microscopy detector. So it is basically you use a detector which works in transmission mode. You can put the detector in off axis or on axis. That means the beam is passing through the sample or the target and reaches the detector directly, or you can detect the scattered beam, which is being scattered from the target material. So these two microscopy modes are called scanning transmission or scanning transmission ion microscopy. Can be both off-axis or on-axis. I will talk about off-axis and on-axis in my later slide. So if you look at these slides, so it shows how we can use STEAM or scanning transmission ion microscopy to image cells, basically, right? So if we look at this is a cell image which is taken using this kind of fluorescence detector. When ions hit the sample, then you get fluorescence out of the cell, and then you see the image or you record the image of the cell inside a chamber, right? Then you have direct transmitted ions, and you detect them using a particular detector, which is called on-axis STEAM, and then you have off-axis STEAM. So the difference from this image, you can see that on-axis and off-axis STEAM, you can actually increase the contrast using off-axis STEAM. So you can see the small particle which are not much resolved in case of on-axis STEAM. So this is the beauty of doing off-axis, right? Okay, the next slide, I'll show rabbit artery tissue. This is a stained tissue. You can see the image or optical image. If you go to the STEAM image, you can see the inside of those cells, which are missing in the optical microscope image. Now we can see more details inside that cell. So if using this kind of STEAM imaging or STEAM imaging mode, you can characterize your sample better, and you can resolve minor details in your samples, right? The next is the comparison between hydrogen and helium ion beam for STEAM imaging. And you can see for hydrogen, the STEAM imaging is not very good, because there are a lot of grainy patches and kind of noisy. You cannot do the resolution is actually bad. Whereas if you go to, and the contrast is also poor. If you go to helium ion beam imaging, you can see a good contrast of that. You can resolve the finer details in the cell. You can resolve the nucleus better, and you can even go into the nucleus and can see finer detail inside the nucleus. So in that sense, helium ion beam works much better than proton beams for this kind of STEAM imaging mode. Now this is another example of another microscopy, which I'll talk later in my talk. And then this imaging is called helium ion microscopy, which is coming up very recently. And this is slightly different than what we do in SIBA. So in SIBA, we use STEAM, which is scanning transmission microscopy mode. Whereas in helium ion microscopy, you use focused helium ion beam and scan over the surface of cell or any sample, right? And then you generate secondary electrons because of the interaction with the primary beam. And these secondary electrons are detected in a secondary electron detector, and from there you can see the morphology of the cells, right? As you can see here. But if you look at the STEAM imaging of the same cell, you can actually figure out where is the nucleus, and inside nucleus you can see the finer details or some black spots which were missing from the helium ion microscopy. So it clearly shows that helium microscopy is good when you are looking for surface of the material, while if you want to see the finer details in your cell or in your sample, you better look at it with a STEAM mode. Okay. Another work that we do in SIBA is called proton beam writing. It's like electron beam writing or writing something on anything, right? Like you write on a notebook with your pen. This writing, like you have a focused ion beam and you write on your on some material called resist, and you create different kind of structures using specific steps. And you can create particularly this kind of interesting structures which are useful for photonic applications. You can even create this kind of structures which you cannot create in using electron beam. The problem with this kind of structure creation is these are very high aspect ratio structure. You can see the wall height is about 1 micron, and you can never go into a material with electron beams that deep, right? So you have to use something else, and since proton beam doesn't spread much inside the material, you can use proton beams to create this kind of structure. And this is the good example that to create this kind of structures of high aspect ratio, which were missing earlier. And you can see there are other structures which you can create in SIBA. So this is particularly confined within the lithography part. I'll talk about another part, which is we have started working recently in SIBA, and this is a very interesting topic. This is called cancer research using proton beam, and it is called proton beam therapy.
Hi, Tanmay. Tanmay, can you hear me?
Yeah, sure.
Yes, very sorry, but the thing is, do you see these marks on the screen?
I actually don't know why they are coming. I'm not doing anything. I'm just moving my mouse.
Someone unintentionally hit the highlight button. Do you have anything on your screen? Because I don't have anything. I can erase it. So I mean, the person who actually did it can only erase it. I see I have no command to actually erase this portion. Do you have anything? No, right?
I can't find it actually. I'll try to restrict myself to move my mouse actually.
If you don't find anything, please continue. I'm so sorry.
The problem is when I move my cursor, these things coming up. So this is annoying, but I cannot solve this problem at this point.
No, then it's perfectly fine. You please carry on. Thank you, Tanmay.
Maybe you can go to your annotation, and then from there you can erase this thing or just clear. On your screen, you can see the view option.
Here all drawings. Okay. I think it's done. Okay.
Yes, this is great. Thank you, Tanmay. Thank you so much. Please continue.
I think should be okay now. Okay, let me see. Yeah, now it is working fine. Sorry for the interruption, right? Okay, I'll move on. So now, so this is the emerging technology which is coming slowly, and it is a big thing in Singapore right now. And Singapore have started, they have started working with this kind of studies already, and they have a center for this kind of treatment, proton beam therapeutic treatment. However, since we have a very focused proton beam in SIBA, we can also do something in there, right? Let me tell something about the X-ray, and that is the normal technique that we use for radiation technology or radiating tumors. But if we use, and what is the benefit of using proton beams instead of X-rays? If you look at the X-ray, it actually, I'll go to this. Okay, so if you look at this profile, this is radiation dose as a function of penetration depth, and you can see the peak is quite broad for X-ray, and it has a long tail. Now the problem with X-ray is that you cannot fully localize your tumor using the X-ray beams, and there is always collateral damage using the X-rays. So there will be live or good cells which you don't want to damage, right? But with the X-rays, you always create some problem with this kind of cells. And the problem with this kind of cells, particularly for children, is that they can grow to tumors later at older ages, right? So that's a problem. So to restrict that or to avoid that, I think one option is to use proton beams instead. So in proton beams, as you can see, because of this Bragg peak, and if you can tune the energy properly of the beam, you can actually go down to your specific depth you want, and you can irradiate or damage the tumor cells which are situated inside your body at a particular location. That is the benefit of using proton beam therapy instead of X-rays. So the problem with proton beam therapy is it is expensive, because as of now we need to create high energy proton beams which can go down deep down into our body. The accelerator is quite big and it's quite expensive. So people are working to cut down the cost for this kind of studies, and probably soon we have some solution in this regard. Okay, so in context to SIBA, what we can do, because we don't have such a huge accelerator, we have an accelerator, but we are restricted to energy of 3 MeV only. But if you want to go deep down, you need even higher energy, even hundreds of MeV. So we cannot afford that in SIBA. Instead, what we can do, we can try with living cells in SIBA and irradiate them and see how we can destroy the tumor cells inside that sample. And that can be done in SIBA using the available beam of protons, right? So in SIBA, the beam line which we talked about earlier, we can use that beam line and we can do living cell irradiation there, and to see if we can destroy the cancerous cells using this kind of high energy proton beam technology. Okay, with that, I will move a little bit from what we do in SIBA, and we'll go to the main theme of the talk, which is basically irradiation of graphene. Now, graphene, we all know, is the ultimate thin material, and it's a wonder material. It creates a lot of noise, created a lot of noise when it was discovered by Prof. Gaim and Novoselov, and they got Nobel Prize. It has its own application for different fields, starting from solar cell, from photovoltaics, from electronics, from photonics. It has all these applications. But I will restrict myself in a specific application, which is called membrane application. So as you can see, because graphene is a single atomically thin layer of carbon, which is hexagonally arranged in a thin sheet, you can use or you can create actually the thinnest membrane ever achieved in this world, right? Using this kind of graphene sheet. And what are the uses or the benefit you can do with this kind of graphene membrane? In particular, you have, when you talk about membrane or membrane technology, you take into account two things. One is permeability or permeance of the membrane. That means how much material you are allowing to go through or pass through the membrane. And the other thing is the selectivity of the membrane. That means which are the species you are allowing to move through the membrane, and which are the things you don't want, and you block those species. So when you talk about membrane, you have to think about these things. And there is always a trade-off between this kind of these two things, the selectivity and the permeability. However, if you look at the graphene research and the thickness that graphene if you use this kind of thin membrane, you can actually overcome the problem of the resistivity of the incoming flux to the incoming flux, and you can increase the permeability. At the same time, if you use some technology and create some openings in the graphene, then you can actually select a particular species of material to pass through the graphene. In general, graphene is impermeable to anything. It doesn't allow anything to pass through normally, right? Particularly even air also you cannot, graphene doesn't let it go through. Okay, apart from that, graphene is very strong material. The Young modulus is very high. Not only that, it is becoming a very interesting material for biosensing because of this thinnest membrane approach, and it can be used for genetic coding or decoding, this kind of applications also. Or what I use here is based on this kind of freestanding on chip, or basically chips we use to give support to the graphene membrane. You can see the silicon nitride membrane is supported by a silicon substrate, and there you have on top you create you transfer graphene. And the beauty of graphene is that you can transfer graphene on any substrate if you want, and then you can make it freestanding as well. It can be supported or it can be freestanding. However, the main challenge with graphene research, particularly from the membrane point of view, is to keep graphene clean, because whenever you expose graphene to the ambience, it absorbs the moisture, it absorbs the hydrocarbons present in the atmosphere, and it gets dirty. So to keep clean, you need some specific process, and you have to optimize that process for this kind of application. By clean, what I mean by clean, you can see in the later slide. You can see here the scanning transmission electron microscope of a graphene, freestanding graphene membrane, and you can actually see the hexagonal structure of graphene, a single layer graphene here. And you can actually see the hexagonal structure of graphene, of carbon atoms there. However, you can also see a whitish contrast where you don't see that good resolution. So by contamination, what I meant earlier is this kind of contamination, which you can see in the electron microscopy. These are very thin layer of hydrocarbons which are deposited on graphene surface. So you have to be very careful when you are handling this kind of graphene membranes, particularly for this kind of membrane application. So now what we can do in SIBA, as I told, we do ion beam related research as well. So the idea is to create openings in graphene, right? And we can use a broad beam exposure to expose graphene, because the ion beam, particularly low energy ion beam, can create vacancy defects. Then we are probably see some defects which is created in the graphene, right? And in general, the prediction for graphene openings has to be less than 2 nanometer to use for water desalination, which I'll come later in my talk. So if you see here, with this kind of exposure to ion beam, you can actually create monovacancy defects in the graphene lattice. You can probably see the contrast, I'm not sure, probably yes, right? And these are the Raman spectroscopic studies where you can quantify what a number of defects which are created, and you can actually measure the different distance between two defects. Okay, so these are all for the broad beam exposure point of view. So, but the problem with the broad beam exposure that you don't have much control over the structures that you have created, and you don't have much control over the damage that you create. The damage can be more than you expect, right? And if you want to specifically or locally create openings in graphene, you have to take another approach apart from the broad beam exposure. So the other approach, which can be a focused beam approach, and here this new instrument comes into play, that is called helium ion microscope. This is very new, and I think only few places in the world they have this facility, and NUS is one of them. So this is called, so if you look at the structure of this whole microscope, normally like in SEM or scanning electron microscope, you can see it has a column where you generate, it has a source where you generate the ions, and then it has a column to focus or to play around with the beam. And from there, at the bottom, you have a chamber and the detector to detect the secondary electrons coming out from the samples after the beam exposure. If you look at the internal part of the helium ion microscope, you can see here the top part is the gun where you have the source, and from the source you generate the ion beam at a particular condition, and then it goes to a set of electromagnetic lenses or quadruple lenses. Then you have different beam optics, and then you let it fall on the on your sample, and from there, from that specimen, you detect the secondary electrons which are emitted because of this ion interaction. The beauty of this instrument is that you can create a source size of a single atom. For example, if you look at this picture, you can only see three structures, like three ball-like structures, and these are nothing but three atoms at the tip of the source. The source is made out of tungsten wire, which is very sharp, and then on top you have only three atoms. And out of these three atoms, you can select actually only one atom, and then you use that atom as a virtual source to generate the ion beams. So if you look at this schematic here, this ion beam, which is coming out from this single atom, and then passes through different kind of apertures, and then interact with the sample and gets detected in the secondary electron detector. This is an image of a freestanding graphene membrane at the bottom on 1.2 micron hole. This is freestanding graphene, which I talked about earlier, and you can see this line which is diagonally connected the periphery of the hole. This is actually the folds. So when you use graphene to transfer, sometimes you don't have a fully flat graphene. There might be folds and there might be wrinkles on the graphene due to transfer problem. And this is one of the examples. So here I show some opening that I can create using this kind of highly focused ion beam. This is an example where I can create a 30 nanometer hole in a freestanding graphene membrane. You can see this black dot, which is about 30 nanometer. And we have used this kind of helium ion microscope technology. Now, the next question, why do we need pores and what is the application of this kind of pores in graphene? I would say the application is, there are a multitude of applications. For example, this nanopores or the solid state nanopores is a big thing. For example, it can be used for DNA sequencing, for biological analysis. You can let the DNA translocate through this single pore and you can get specific information which can be used for genetic coding. Then this can be used for energy harvesting, which is slowly coming up, but you don't get very high efficiency or high wattage out of this kind of technology yet. So people are working on this kind of technology. Different people are working. There is the filtration based technology, which normally I use. So filtration means we use different kind of gases to filter out and to see what is the performance of selectivity and what is the performance of permeance using this kind of membrane. There is another big topic which was predicted very recently, I think 2012, that graphene membrane can be used for water desalination, and people have jumped into it to try if it is possible. And there are many efforts for this kind of technology to desalinate water, because as my previous speaker mentioned about the renewable energy sources, apart from the renewable energy sources, there is another global concern, which is the water scarcity. And if you look at a recent Niti Aayog reports, they have already predicted that by 2030, India, 40% of Indian cities will be suffering from dearth of water. So this is a big concern. And if we don't act at this point, it might be very late. And we need to have some alternative technologies apart from the regular reverse osmosis or this kind of technologies, which are more expensive, particularly from Indian point of view. So with this, I would summarize my talk. So we can use MEV focused ion beam for high aspect ratio structures. We can use ion beam irradiation technique for creating defects in 2D lattice. And this kind of defects or single vacancy or mono vacancy defects can be used for water purification, because for water purification, the defect range should be, the efficient defect range should be within 2 nanometer in size. So if you can tune the pore size within 2 nanometer, that would be great. That would be the holy grail of the whole research. In that sense, helium ion microscopy can be a good candidate for pore drilling. It is a direct drilling technique. You can play with the parameters of the helium ion microscope with the helium ion microscope, and you can create different size of pores. It is fast. It is and the vacuum level is very good. So you don't create too much of contamination on your surface on the surface of the material. And the solid-state nanopores, as I told, it's not explored to its greatest extent, and there are many opportunities which are still lying with this kind of technology. With that, I want to show you this picture which happened last year summer in Chennai, and you can see the people are already under water stress, and India is one of that country which is under water stress already. And one solution to this problem can be to understand the basic filtration and this kind of approach using this kind of ultimate membrane, which is graphene, and probably this can lead to the solution of this kind of water problem in the future. The take-home message I would like to mention with ion beam, you can have a plethora of opportunities in material science. Not only in material science, you can diverge this technology to a biological application, to different kind of other application as well, for radiation technology and all this. But the negative is it is expensive, and it is very expensive to maintain the facility, of course. The second point is the safety concern. As you go high in the energy, you create a lot of radiation, particularly X-ray and this kind of radiation. So you have to suppress, or you have to have the way to control those kind of radiation to interact with your body. So there are safety concerns with this kind of approaches as well. With that, I would like to thank Dr. Amit for inviting me for this webinar, and I hope you all like this talk. With this, I'd like to acknowledge my collaborators, and I am open to any questions at this point. Thank you very much.
Great. Okay, thank you. Thank you so much, Tanmay. And I hope everybody really enjoyed this intriguing talk, because this covers high energy physics and like the ion beam applications and graphene, definitely water filtration. Then it also covers a lot into instrumentation. I mean, some of these things have been very fascinating. I think like since my childhood, I've been very fascinated by high energy physics, and then I came to know about graphene. And I think you bring in the biological applications as well. So that's great. Really, thank you so much from everyone on this, on the speakers and our organizers. I'd like to thank you on this. We don't have much time on this. We have about 5 minutes left on this session. So I'd like to ask the same question to you, so that because it's more like a career outreach program. So I'm just hoping if you can elaborate into this field, like the field of instrumentation, high energy physics, and maybe graphene. I mean, what do you think the scope for the students and the researchers?
Okay, thank you for this nice words, Amit. First of all, I would like to say this is not actually high energy physics, but it is kind of a branch of material science itself. If you look at the chips that you use in your mobile phones or any kind of electronic devices, all the small chips, they contain a bit amount of this ion beam technology, because you need to dope those this kind of chips using different kind of ions, right? If you want to dope P-type ions, or you want to do with N-type ions. So all this semiconductor technology is based, particularly the foundation starts with the ion beam technology. It's a part of material science research, or the material modification part comes in this picture. So from the career outreach part, I would say ion beam is a very well studied topic already. People have studied it for long, and it is quite optimized. But if you look from the perspective of graphene, since this is a new material, and there are not much investigations with how this kind of 2D materials, apart from graphene, also there are other 2D materials. The ions interact with this kind of 2D materials. So there is a still gap between this kind of ion matter interaction, and we need to fill up this gap, because unless we know the how it interacts with these kind of ions, we cannot really apply to the next level or to the industrial level. So the basic fundamental research has to be there in order to understand the basic physics, which is behind these kind of techniques or this kind of instrumentation. And of course, after that, that can be translated later in the industrial research. For the students particularly, I would say graphene is the emerging field of technology. You can have various approaches or various research topics that you can choose. And I would say for graphene or 2D materials, the sky is the limit. I would say there is no limit at all for these kind of materials, because people have started growing not only graphene but other materials which are electronically important, and you can create you can stack different kind of 2D materials to create your desired properties in a heterostructure. So these are emerging fields which are coming slowly. Of course, there is membrane technology also, which is not optimized at this point. So these are kind of nanofluidics and microfluidics application that is still open for further research. So if you look at the Oxford Nanopore, which is a very new company, they do this kind of DNA sequencing research. They have now a revenue of $2 billion, and that happened probably within 3 years or maybe 5 years at least. So this shows that how rapidly this field is growing, and probably over within a decade, probably it will reach to a new level. And there will be a lot of scopes for the newcomers.
Great, thank you. Thank you so much, Tanmay. And I'd like to personally thank you again and Jayaprakash sir for attending this session. As we switch to the next session, which is in another 30 minutes, we'll have a short break for 30 minutes. And so thank you again, Tanmay and Jayaprakash sir, for like giving us this opportunity to have an interaction with you. And we do understand there is a lot of interest in NUS, in this fields particularly also, that many people want to work on that, and they would probably reach out to you. It's the easiest is like Google your email address and shoot you an email. We very much appreciate that if you can interact with them in the near future. So from the organizers and from the college principals, everyone, so I'd like to thank you again, Jayaprakash sir and Tanmay. We'll switch to the next session. We'll give a break for 30 minutes. I'll just give you an idea what comes next. And because we had too much of technical talks already, what we're doing next is we are switching to a bit non-technical, but the person is very much technical. He is the president and CEO of Arhan Educon Limited from London and UK. And this talk is more about building resilience in higher education through global collaborations. So Mr. Prasanta Sao sir would be speaking more about institutional collaborations with many universities in UK, and definitely it's more towards the students, how they can reach out to the universities in UK and other places. So please join us again in another 30 minutes at 2:15. And probably I'll keep this session on, but for next 30 minutes, just go have your lunch, take a break, and let's meet again. Thank you again, everyone. Let's meet very soon in another 30 minutes. So 2:15 we are meeting again.